You're Levy?
Yeah.
Okay. And you are?
James.
James.
So, due to some interesting feature of the post office that I should know about, but I don't, they didn't deliver the camera. So my iPhone's being used to take this. I have no way of knowing what time it is, so if people would let me know about halfway through the class and maybe give me a 5 or 10 minute warning at the end of the class, that would be helpful. Well, we're not all here, are we? It's not quite, it's a few minutes before 55. All right, I'm gonna just start taking minutes out. Laryl? Daniel? Giuseppe? Kevin? Okay, Suyon? Matthew? Yeah, I'm doing my can to burn your faces into my head. Isabella? Okay. Lynn? Is Lynn here? Okay. Kayla? Oh. Caitlin? Joseph? Devin? Tony? Calvin? Karina? Okay. Cal? Is Cal here? Zarina? And Frankie? Okay, I didn't say your name, tell me who you are. Again?
Ariel?
Yes. And there's, yes. Calvin, okay. All right, so, someone, okay. Those as you walk in, tell me who you are so I can walk you in. So you're Giuseppe? No. No, okay, somebody else. Your name is? not you.
Antonia?
Huh? You're Tony, right?
Yeah.
It's misspelled.
Oh, and who else did I miss? Kevin, is that? Okay, so I still don't see Seppi, Caitlin, Joseph, Devin.
Done.
Oh, okay. And Zarina.
Zarina?
Oh. All right, I'm gonna pass around, oh, this isn't gonna work, is it? Well, do what you can. It's got 6 lines for the 6 rows, and it's got room for 6, but there's 2, 4, 6, 8 in that row. So you're gonna have to pass it around, write your name where, so you're sitting here. And, you know, this isn't, we're not in prison, but try and sit in the same seat. If you want to change it, you can do that. If you're going to change it permanently, maybe let me know. Okay. Why do that now? Okay, so I like this here. Rearrange the furniture a little. All right. Okay, first things, for Tuesday, this is next Tuesday, the 31st, there's an assignment. On the website. It has 2 parts. Part 1 comes from Stuart. If you don't have Stuart yet, and that's going to be a problem, maybe come see me in my office hours and we'll try and fix that. And then there's a second part which you just print off. And it's not from Stuart. So that's, you have the weekend. You are.
Do something.
See, with the masks on, to me, he looks just like you. So, no offense. All right. So we were talking about limits. And thinking about this over Wednesday, and on one hand, you're not going to have to know the mechanics of the delta epsilon proof. We're going to see a couple of them anyway, some simple ones, but you've got to try and get a feel for this. A lot of calculus, a lot of it's nice and easy because it's mechanical, but you know, like all of math, you know, if I give you a formula, oh sure, that makes things easy, but when you see something you haven't seen before, what? You know, you don't necessarily learn how to wander around in math land. So I want to just try one more shot at, you know, what a limit feels like. And we're going to do something a little different. We were doing functions, but I want to look at a series. And the series I want to look at starts 1 over 1, goes 1 over 2, 1 over 3, 4, and it just keeps going. And it's easy to describe this mathematically. You've just got 1 over n, and we're going to look at the limit as n goes to infinity, as n gets bigger. And n in this case is just an integer. You don't have to worry about all the numbers in between. This is something, you might study in some future math class, limit of a series, but it's not really that important. What I want you to think about is, well, clearly, where is this going? And further and further out we get, the closer and closer it gets to 0, yeah. And so we intuitively can see that the limit of this is 0, but yet, no matter how far I write, I could be writing for eons and eons, I'm never going to get to 0. And 0 is it's a unique number in the number system. You multiply anything by 0, you get 0. So it's interesting. So we want a way to describe this, and we're going to describe it pretty much the same way I talked about yesterday with the delta epsilon. So, except this can be really easy. See, I'm going to say, if I give you some epsilon, which is greater than 0, what I want to know is, what delta is there so that, n equals delta, such that 1 over n minus 0, my limit, is less than epsilon. Okay, let's unpack that a little. So my numbers are, this sequence, and they're getting close to 0. Okay? I don't need an absolute value here, but we're going to leave it in anyway. And we want to know what, if I give you an epsilon, I want you to be really close to 0. What's the delta I need for n? Well, let's say I give you an epsilon of 0.001. How can I guarantee that this is less than 0.001? What n is going to do that? I'm going to make it a little easier. You say less than or equal to. Can I just let n or delta be 1 over 0.001? Or, I guess if I make it anything, I can get rid of the equal sign if I just make delta less than 0.001. So I can say 1 over 0.001 times a half. So, I don't know if I'm saying this well. It's not a matter of, it's just a matter of finding this delta that causes this to squeeze that close. We're going to do a little bit with this, not with a series, but with the delta epsilon stuff today. So I just want you to have a feel for it. It's just a matter of, we want to get so close, and we have to find some value here that gets us that close. And if we can always do that, then we have this limit, and we know that the limit is 0. Take a breath here. Okay. Any questions about this? I'm just, again, this is just,
you don't understand something, just throw it at me. Try to work through this. Yes?
What exactly is like epsilon and delta? What do they represent?
Okay, good, because I'm sure there are other people here kind of going, I don't know what he's talking about. Okay.
Well, epsilon is a variable.
Except it's one that, we could think of it as as a challenge. You get to decide what epsilon is. You're picking small epsilons, and what you mean is, I want something in this series to be as close to 0 as epsilon. Right? So, I don't know. Let's do an example. Epsilon is 0.0001. So I want to know at what point this series is going to be closer to 0 than this. So I'm going to pick n as, well, 1 over this is, it's 1,000, but I'm just going to say 1,001. So you gave me this number, and I say, well, go to n equal this, right, out here. And now I'm closer to 0 than what you asked for. Now, you can add another 0, and I can add another 0. You see, I can always do that. I can always make it as, you can write a very big number here. You could say 10 to the minus 100. And all I have to do is say, okay, that's 10 to the 100 plus 1. Now 1 over this is closer to 0 than you asked. Now, you say, well, we never get there. And that's right. A limit is not about what happens at some point, at infinity, or in the cases we're talking about at some value. It's about getting as close as we want to some value. Again, this is kind of it's an odd kind of thing. Usually in math, you're thinking of something being exactly something. The limit is exactly 0, but nothing in this sequence actually reaches 0. That help any? Okay. I don't know why I'm having trouble breathing here. I don't think it's lack of oxygen. It's just me. Okay. Before we get moving, any other questions, things about the class before? Okay.
Is it homework? Is out or
Is homework what?
out? Through out, or is it like printed out on
I apologize. I'm just not hearing.
the homework? Is it printing it out?
Oh, okay. Yeah, I haven't said anything about this. When you turn in your homework, it says something about it in the syllabus. I'm kind of old school. It's not online. You just, you do your homework. You put your name on it, please. I don't know, upper left or upper right-hand corner. If you have multiple pages, it's best to number them and staple them together. It's not absolutely required. You certainly can number them. You might not have a stapler. If you don't have a stapler, put your name on each one, because people will hand me piles of paper and they'll get shuffled, and we want to keep it together. And again, you want to try and get it done Tuesday. As I said, if you don't make, if something comes up, don't sweat it. When you have a chance, this is practice. I will post solutions probably on Tuesday, and when you get it back, you can check them too. And it's perfectly legit to come into class and say, hey, I was doing this problem, I don't get it. Or how do you do this one? Or I got this wrong, why? And you can either do that in front of the class so everybody can learn, or if you don't feel like that, come to the office hours and do it there. Okay? Okay, so what we're gonna do today is to learn about calculating limits. As I pointed out, that definition of a limit doesn't tell you anything about getting the limit, finding the limit. It just tells you if you have something you think is the limit, here's how to prove that it is. So we need some mechanics. We need actually some theorems that are going to help us. So to do that, we're going to start off with a few very simple limits, and we're just going to see how they fit into the definition. So first is limit as x approaches c of c is c. In other words, here my function f of x is a constant. Actually, this doesn't even have to be c. This could be just, let's say, a. So how does the proof go? Well, we need to pick, given some epsilon, we need some delta such that x minus c is less than, I don't want to say x, I want to say c, because that's our function. This is our function, this is our limit, is less than epsilon. Well, what delta am I going to pick to cause this to happen? Pick any delta you want, right? Doesn't matter, right? Automatically, this is 0, which is less than epsilon. So that's kind of easy. This will work this way. Okay. The next one we're going to do, I'm going to number these. It's a little more complicated. Yes.
Could you go over that last one again?
Sure. And let me make a point here. Sometimes the most simple, obvious things, you just have to stare at them and then you go, oh, duh, right?
Mm-hmm.
But until you do, it's very hard because it's so abstract. Okay. It might help if I write down limit, this is definition of f of x. X approaches c equals L. If and only if, for, I don't know if you've seen this math syntax before, for all epsilon greater than 0, there exists a delta such that x minus delta, I'm sorry, see, I'm in front of the blackboard, so now I have to think without writing. For x minus delta, now, x minus c
less than delta, f of x minus the limit is less than epsilon. So let me try and go over this again. We pick an epsilon, we're trying to show that our function is now really close to the limit, within epsilon of it. This says there is some delta that we can squeeze the x close enough to see that this is the case. All right. So again, that's a little hard, a little abstract, but let's take this example again here. My function now is a constant function. As I get here, in this case, close to some value, I want to know that c is within epsilon of my function c. But it's already really close. C minus c is 0. So no matter what epsilon you pick, greater than 0, I'm already there. I can pick any delta. It's kind of a non-use of this definition, by the way. Does that help?
Yeah.
Okay. There are others out there who are very thankful you asked. I know. Yes?
What does the backwards E mean?
Okay. These are quantifiers. This is the universal quantifier, it means for all. And this is the, I forget the word. This just says there exists one. There exists at least one of these.
Okay.
So again, with a limit, you have this, and if you have this, you have a limit. Okay. Maybe the one that's the next one, which is a little more complicated, but still pretty easy, will make more sense. We want to show that the limit, as x approaches c, of f of x is x, is c. Okay. Draw a little graph. So here's my function, f of x equals x. And we have some value c here. And we have some limit, which is c. And we want to show that given some epsilon, we want to get close to c, that there's some delta that I can squeeze, this x into this interval that will force the limit to be within epsilon of c. This actually kind of sounds almost dumb. It's like, of course it's going to be c, right? What else could it be, right? But again, we're just going through the mechanics and see how these things work. Okay. Usually to solve these, when they're more complicated, you have to think and work backwards. But here it's really easy. We just set delta equal epsilon. Because if x minus c, the absolute value of x minus c, is less than delta, then the function of x, which is x minus L, which is c, is less than epsilon. You see that? I said delta equal to epsilon. Well, if I put epsilon here, then this is going to be true. It's just obvious. Okay, so I'm gonna transfer that over here, because this is, we're doing baby steps now. We're gonna build up some equipment so we can do more interesting things. So limit as x approaches c, and x equals c. Yes?
Can you use like actual numbers? I think that would help me. Like for
No, I'm not laughing at you. Yes, I will. But
or for like the new followers.
I'm reminded of a story a friend of mine told me. He was a math major in college. I wasn't. And he had this professor
and he says to the professor, can you give us an example with numbers? And he goes, you know, he's like, you know, some theorem, you know, blah, 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 you know, for all n, you know, dot, 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 dot. And it all says, can you do that with a number? And he says, oh, sure. He says, you know, theorem for all n, dot, 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 dot. I'm sorry, it just, like, I guess when you're around math people enough, you'll understand. Like, what? A number? Okay. Let's say we want to show that the limit as x approaches 5 of f of x, where f of x equals x, is 5. Now, let me digress for a second. We have a function, and you know what it seems like is sometimes to find the limit, you can just plug in the number. Yes, not only sometimes, a lot. We're gonna get to that later today. There's a lot of functions you can do that with. Perfectly valid. Okay, so what I want is if you give me some epsilon. So let's say you give me 0.1, that's a nice small epsilon. I want to find a delta such that making x minus 5 less than delta implies that f of x, which is x, minus the limit 5, is less than epsilon, which is 0.1. So the question is, what delta do I have to choose such that if I have x minus 5 less, absolute value of x minus 5 less than delta, I'm within, you know, delta of this, that this is true. Stare at you should see that. Stare at it until you see it because it's so obvious, right? You just choose 0.1. You just choose delta equals epsilon. Okay? I know this is in a way it's maddeningly simple, yet it's weird, right? Okay. When things get more complicated, it probably will make more sense. All right, so we have this. All right. Now we're getting just a little more complicated. We want to show that the limit, and unfortunately a little more abstract, of if the limit of f of x as x approaches c is m, if this is true, we have a limit, then the limit as x approaches c of k times f of x is equal to k times m. Okay, what are we dealing with here? We're saying if we have a limit, some function, you know, as you get close to c becomes m, that if you substitute another function, a constant times that function, that the limit is just k times m. But you can move constants in and out of this limit. I guess it might be nicer to write it this way: k times the limit as x approaches c of f of x. Now, this is harder to absorb because I haven't told you what f of x is. I'm stating this is true for any f of x. And, you know, you can like, if it helps, you can plug in your favorite function. You know, sine of x, cosine of x, e to the x. Everybody has a favorite function, don't they? Okay, so how do we show this? Well, because of this and the definition, we know, if I choose, if I choose some epsilon greater than 0, then I know there exists a delta such that x minus c less than delta will imply that f of x minus our limit m is less than epsilon. We know this, that's our given here, right? We want to show this. So now we want to pick a new delta to show this limit is true. Well, what we can do is we can choose delta equal to this epsilon over the absolute value of k. Well, why are we doing that? Well, now we have x minus c is less than epsilon over k. And what we want to show is that k times f of x minus k times the limit, right? That's what we're trying to show here, is less than epsilon. Well, how do we get from here to here? Well, we multiply both sides by the absolute value of k. And I can take the absolute value of k and move it inside this absolute value sign. Did I do that right? I don't think I did that right. I'm sorry. Made a boo-boo.
I have a question.
Yeah.
Wouldn't it be delta over k instead of epsilon over k in that section down there? Oh.
Well, okay. Yeah, this delta, we'll call this delta 1. So if our delta is now delta 1 over k. Yes, that's right. Made a
Just
boo-boo.
keep the thing.
Yeah. This is where I would be much better at 9 at night than at 9 in the morning. Oh, I'm sorry. Let me try again. I guess since we know epsilon is greater than 0, we know that epsilon over k is greater than 0, right? So we can find, by our assumption, we can find a delta, there exists a delta, such that x minus c less than delta implies
f of x minus m is less than epsilon over k. All right, in other words, we're just, instead of the epsilon we used up here, we're just using epsilon over k. All right. I'm not saying this very well, I know. That's the problem with these things. You can kind of get lost because they're kind of backwards. All right, well, from here, it's easy to see that k f of x minus k m is less than epsilon, which is what we wanted, which is, again, that's our definition that the limit of k of f of x as x approaches c is just k times this. All right, yes?
So you multiply each side by k so that you turn it into the other function?
Here, I'm multiplying both sides by the absolute value of k.
Okay.
We're just trying to keep, you know, I mean, if k could be a negative number, and it still works, right? But if I'm not explicit, then, you know, my inequality is going to switch. That's why I make that. It's also, you know, if k is negative, then epsilon over k isn't greater than 0, it's less than 0. So I have to keep that straight. Yes?
Where did the m
The m? The m comes from back here. You're given this limit is m. Usually I'll use L for the limit, but this time I just used m. All right, so number 3, that's a nice tool we have. When you're doing limits, constants don't matter. We're going to see this in a number of instances, something like this in calculus, where constants kind of move in and out of the function very nicely. Okay, there are 2 more tools I want to give you. Having failed badly on the last one, I'm going to foolishly try one more time to show you a proof, and then I will leave you so that you don't have to you know, lose sleep over these. Okay, so number 4 says if the limit as x approaches c of f of x equals L, and the limit as x approaches c of a new function, g of x, is some other limit, m, then the limit as x approaches c of f of x plus g of x equals L plus m. So this tells me if I have 2 limits that I know, and I create a new function, which is their sum, that the limit for that new function is just the sum of the limits. Let me abbreviate that. The limit of the sum is the sum of the limits. Well, how do we prove this? Well, what we want to do is we want to take our epsilon, and we want to show that we can get within epsilon of L plus m. 1. F of x plus g of x minus L plus m to be less than epsilon. Well, we know that we can pick an epsilon because we have 2 limits here.
we can pick an epsilon that we can get these close to their limits. So let's call them epsilon f and epsilon g, and we're just going to set those to epsilon over 2. So I know that I can get f of x minus L less than epsilon over 2, and I can get g of x minus m less than epsilon over 2. I can add these two together, yes?
Why did you get epsilon over 2?
Because it's like in Jeopardy, because I already know the answer. It's, I can pick anything I want. I could pick epsilon over 10, or epsilon over 100. What I'm doing is I'm saying, I already know this limit exists. So I already know that I can squeeze this as close as I want to L. Question is, how close do I want to squeeze it? I want to squeeze it epsilon over 2 in both these cases, because now I'm going to add these. And when I add them, on the right side, I'm just going to get epsilon. So here I'm going to have f of x minus L plus g of x minus m. And now the only thing you have to realize is that there's this theorem called the Triangle Theorem, which says that this, that's f of x plus g of x minus L plus m, that this is less than this. In other words, I guess maybe I should establish this first. Less than or equal to. Well, why is this true? Well, if A and B are positive, it's obvious. If one of them is negative, it's kind of obvious too. If both of them are negative, it's kind of obvious. If they're both positive, you get equality. If one of them is negative, then this side is going to be greater than this side, and you get less than. And if they're both negative, you're going to get equality too. Okay. We're kind of going to leave this area of peculiar epsilon delta proofs for the moment. Again, they're not going to be on the midterm or the exam. This is more kind of a demonstration that this fits together. But I'm going to add a few more rules here, and then we're going to take a look at how useful these can be. Okay, this is going to seem kind of intuitive and obvious too. The limit of x as x approaches c of f of x equals L, and the limit of g of x, didn't write that very clearly, g of x equals m, then the limit as x approaches c of f of x times g of x is just L times M. It says if I have two limits, and I create a function by multiplying the functions, that the new limit is just the product of the limits. So the limit of the products is the product of limits. All right, let's show why that can be really helpful here. Say I take the function x to the n. Well, I already know that the limit as x approaches c of x equals c. And I know that this product exists. So I can write the limit as x approaches c of x to the n as the limit as x approaches c of x times the limit as x approaches c of x to the n minus 1. Well, we know what this is. It's c. And we know that, well, what do we know about this? Well, we can just keep repeating that, right, until we get to 1. So this is going to be equal to c to the n. So we have that limit of x to the n, as x approaches c, is just c to the n. Now, if you think about that, I did that with a function I know, x. But I could do it with some other function, f of x. I could do the same argument. Well, I guess I have to say the limit of f of x as x approaches c is L. And the limit as f of x to the n as x approaches c is L to the n. Okay. Let's just go one step further here. Let's say f of x is a polynomial, meaning it looks like this. It's like a to the n, x to the n, plus a to the n minus 1, x to the n minus 1, all the way down to a0. Well, all these theorems here tell us that, you know, the sum of the limit is the limit of the limit of the sum is the sum of the limits, and the same with the products. So really, the limit as x approaches c of some polynomial is just p of c. So this is great, because now whenever we're trying to find a limit and we have a polynomial, we can do that knee-jerk thing we really want to do. We can just plug in the value. All right. Do people come to class with paper and pencil? I hope they do.
let's everybody just try this. What is the limit as x approaches 1 of 5x squared minus 12x plus 2? Not looking for a proof here, I'm just looking for what the limit is. Okay, this is just a simple, you just have to plug in, okay? So it's 7 minus 12 is minus 5. Okay, what time is it?
10:46.
It's 10:46, nobody stopped me to do a break? Oh well. No wonder I'm sweating up here. Okay, well, let's try something a little more challenging. Let's take a look at the limit as x approaches 0 of x plus 3 squared minus 9 over x. Oh, wait a minute. This is not a polynomial. It's a rational function. We plug in 0 here, we get 9, minus 9 is 0, and here we get 0. So it's not entirely clear, is it? Well, okay, let's simplify here a little. This is x squared plus 6x plus 9 minus 9 over x. 9's are going to cancel. We have x squared plus 6x over x. And I'm going to factor here x times x plus 6 over x. Okay, now we can use this product rule, because we know this limit, right? The limit here is going to be the limit of x over x as x approaches 0 times the limit as x plus 6, with x plus 6 as x approaches 0. Well, we haven't talked about this today, but is it obvious what the limit of x over x is? What does this get close to as x gets close to 0? Yeah, it gets close to 1. Remember, we don't care what happens at 0, right? We just want to know what it gets close to. So this is 1, and here we just have a polynomial. So it's 6. All right. What time this class ends at? Oh,
I'm sorry, you know, I'm getting mixed up. Why don't we take a break? Can we take a break for 5 minutes? Did Joseph come to class? Is Joseph here? No, okay. And Caitlin? Can I have that, that sheet back? Ah, thank you. Okay, see if we can make this out. Oh, great, okay. So, all right, thank you. All right, I want to make a remark about math, this class in general. Some of it is, you know, it's conceptual. Some of it's a little mechanical. Like, this stuff can all be kind of mechanical now. I give you a problem, find the limit of this, and it fits one of these. You can kind of use your algebra skills and throw me an answer together. I will try and avoid, what will I call them? They're kind of like math competition questions. They're really hard until you know how to do them, and then they're easy. And I go out of my way to not put things like that in a high pressure exam where all I'm doing is testing whether, you know, you'd be a good candidate for the math team, right? However, you might run into some of these with the homework, and it doesn't hurt to kind of get an intuition, you know, where to look for an answer. So here we have an example. What is the limit as x approaches 0 of the square root of x squared plus 9 minus 3 over x squared? Well, you look at that and say, well, okay, at 0, this is 9, which is 3 minus 3 is 0, and the denominator goes to 0 too. But we don't have some nice rule that kind of explains what to do here. So maybe we can't do it, or maybe there's some way we can kind of get to this answer. And I think that, again, I'm not really trying to train you guys for the math team, but the thing to focus on here is, well, this is kind of ugly, square root. And it'd be nice if there'd be some way to get rid of it. And here we fall back on, you know, there's some patterns that maybe some of you already have them etched to the back of your head. But there's a very important pattern from algebra. Is a squared minus b squared equals what? How do I factor that?
A minus b, a plus b.
Yeah. Now I hope what we have here is one student who's not shy and knew the answer, and everyone else was just being shy. If this isn't like, doesn't just pop out at you, maybe come see me at office hours sometime. We'll go over a few things that are like this that you should know. Okay, so how's that going to help me here? Well, let's try multiplying this by 1. But a very specific one. Everybody see how I got that? I want to get rid of this square root here, and I know if I square it, everything will be happy. I mean, I'm going to end up with it in the denominator, but let's see what happens. So I get a squared, a minus b times a plus b, so that's a squared, which is x squared plus 9, minus b squared, which is 9. Okay, and then on the bottom I have x squared over square root of x squared plus 9 plus 3. Okay, and I'm trying to find the limit as x approaches 0. Well, we need a new rule. We're going to get a new rule in just a minute. It's going to help us. It has to do with quotients. But you can kind of see, right? What is this going to? This is going to 0 plus 9 minus. Did I get it right? I did. It's going to 0. No, that's not right. No, it is. Okay, all right, that's fine. It's going to x squared, right? And what have we got in the denominator? X squared times square root of x squared plus 9 plus 3. All right, so the top and bottom are still going to 0, but look, we can rewrite this. This is x squared over x squared times 1 over square root of x squared plus 9 plus 3. Again, the limit as x approaches 0. Well, you know what x over x goes to? It goes to 1. So x squared over x squared is x over x times x over x. We have our product rule. This is going to 1. And here, what do we have? 1 over square root of 9, that's 3 plus 3. Oh, it's just 1/6. Whoa. You can do that. So you're going to find, not intentionally, you're going to find some of this in the homework where you're going to have to like figure out some trick. Right? Don't be put off by that. I mean, try and see, is there some pearl of wisdom in this trick? I think here it's obvious. It's like, we can move stuff around the numerator and the denominator in a productive way by this trick. Okay, so let's look at our next rule. It says the limit of f of x over g of x as x approaches c is equal to f of c over g of c, but not quite. Only if g of c is not 0.
have the limit as x approaches 0 of x squared plus 5 over x times x minus 1. Well, the top here is going to 5, this is going to 0, so this doesn't apply. I mean, what would it mean? 5 over 0. You can't do that. And as you saw in the previous two examples, if both f of x and g of x go to 0, maybe. Then we actually have to do some work to see if there's a limit, find out what it is. Okay. All right, I have another example here I want to try before we move on. Okay, everybody can try this now. What is the limit as x approaches 2? X minus 5 over x squared plus 1. All right, anyone want to throw out a guess? 1/5. Well, 6 minus 5 is 1. 4 plus 1 is a fifth. Pretty straightforward. Right? That was pretty easy. Let's try the following. Limit as x approaches 1 of x squared minus 1 over x minus 1. Take a minute. Anybody need any more time? Okay, a side comment. there's this thing that I've seen high school teachers and college professors do in math classes, which is they find problems to put on their exams that they don't really think it through. Like, might be something like this. I mean, this isn't that tricky, but you know, it has some trick that you could just dive in and spend, you know, not everybody just gets it right away, but you could get it. You could do everything on the exam, but then they squeeze you into like an hour or however long the exam is, and they put people under pressure, and then all of a sudden, like on the spot, in front of the, you know, it's like you're in front of the audience, and you can't think straight. I won't point anyone else, but you know, I've seen a few heads nod. Yeah, we've all had that experience. I just want to say, I'm very aware of it, and I do not want to test whether you are some kind of lightning fast math whiz. I want you to learn the material. So you should know when you come in to take an exam that I've spent a lot of time focusing on, did you learn the material, not, you know, not are you an ace. You still want to, you know, you want to go on in math or science or whatever. You're going to be doing math. You want to get those skills as up as, you know, where you can. You want to, you know, learn these little pearls of wisdom. But I don't think you should be, you know, quizzed on them. So, okay. So, someone want to tell me what to do with this? Anyone know it? How we're gonna? Yes.
I got 2.
You got 2. Oh. Okay. I want to know how you got 2.
I simplified the x squared minus 1 into x plus 1 times x minus 1.
Right, and there we have. This goes, I mean, it goes to 0, 0, but clearly x over 1 over x minus 1. We can make that as close to 1 as we want. And then this is our polynomial, so it's 2. Thank you. Okay. That's the easy stuff. There's just a little bit more that's not as easy. Well, I don't know. The first one's not that hard. There's one more tool we have in our. Am I going to fit it on the board here? That is the limit as x approaches c, f of x equals m, if then limit as x approaches c of the nth root of f of x equals the nth root of m. Oh, that's not so hard. You can see where that could be useful. You have some limit approaches, I don't know, 5 of 3x squared plus 2x plus 1 cubed root. Well, this is just a polynomial. We can just plug 5 in here and then find the cube root of it, right? That's not the hard one. I hope I gave you some problems that use this next theorem. It's really beautiful what you can do with this, but it's kind of tricky. And this is called, depending upon which book you read, this is either called the pinching theorem or the squeeze So, we probably need to draw a little diagram here to illustrate this. So we have a few functions here. We have some function f, and we're interested in the limit f of x. No. We're interested in the limit as f of x gets close to c. So that's what we're interested in. But we have a problem evaluating this. When I give you an example, you'll see what I mean. But within some kind of p, some distance p of around c, we know something about two other functions. We're going to call them g of x and h of x. I guess I really need a different color here, don't I? That would be helpful. All right. So I've got my orange g of x, my blue h of x, and my black f of x. And I know that when I get around c, there's some value that I can get around it for which the following is true. H of x is less than or equal to f of x, which is less than or equal to g of x. I mean, outside of this p, it doesn't matter, but this could, go all over the place. Doesn't matter. But within some bounds, I have this relationship. And furthermore, I know that the limit of h of x as x approaches c is L, and the limit of g of x as x approaches c is L. If I know all this, then I can say for certain that the limit of x approaches c of f of x equals L. And this is called pinching or squeeze, because our function, the one we're interested in, gets squeezed between these functions. These functions have a limit. They're going to get ever close to some value L, maybe from the top and from the bottom. And our function is in between, and we know then that our function has that same limit. Now, this is really great because there are some limits you might want to calculate that are kind of obnoxious looking. Let's take a look at one. What if I wanted to find the limit as x approaches 0 of x squared times the sine of 1 over x? The sine of 1 over x, as x gets close to 0, 1 over x is going to get large, so it's going to be kind of going up and down like crazy. So kind of hard to find the limit. So what do we want to do here? Well, we want to find these functions h and g. This is f of x. Well, for g of x, how about x squared? We know the sign of x can only go between -1 and 1, right? So x squared will always be, g of x will always be greater than or equal to f of x. For h, we're going to use -x squared. Because, even when the sign gets down to -1, then we're just equal. So h of x is always less than this. Guess I'm going to write that out. -x squared less than or equal to x squared sine of 1 over x squared. So if we evaluate the limit as these approach 0, and fortuitously it's the same limit, right? You need this. You need them both to go to the same limit. Well, limit as x approaches 0 of x squared is 0. The limit as x approaches 0 of -x squared equals 0. So now we know that our limit has to go to 0. Turns out this obnoxious behavior of this function, as it gets close to 0, it's going up and down very quickly, but less and less and less. And it will go to 0. So sometimes this comes in handy. Of course, you have to be able to find a g and an h, and you have to be able to evaluate their limit, and it has to be the same limit. If not, this theorem is useless. All right. Okay, you'll have some fun playing with the homework, I think, on these. I think we have some time left, but I think this was kind of a meaty day. We're gonna stop now. I know it's what time is it now? 11:22. Okay. Those of you who have questions about anything can come up and ask. Those of you who want to take a break for the rest of the class, you're on your own.